In this section, we begin to discuss Taylor series, a special type of series. In first section, we discussed Taylor polynomials. So the only difference is the series is there are infinitely many terms. They will never stop, right? And this is the formula we are going to use. A special case is when A is 0, which is so-called the Maclaurin series. And we practice that in class for all these problems. So now we are going to try to find a Taylor series for a function, which is this 1 over 1 minus x, center at a equals 3. Let's just try that. So in this particular problem, we want to find those CIs so that 1 over 1 minus x can be written as a Taylor series center at center at 3. Now to save the time, and I kind of worked out the problems first, and then let's go through that line by line. This is the formula we are going to use. Here, this is the expanded form, and this is just the summation form. They're the same thing. Basically, in this particular problem, we need to figure out those CIs, right? C0, and actually you can already see that C0 is this guy, f of a. And C1 is my f prime of a. And C2 is f double prime of a divided by 2 factorial. And C3 is f triple prime at a divided by 3 factorial. So I need to find those. So you can see how I lay out my work. The first column, I'm gonna find all the derivative. So these are all the derivative. I begin with f of x, which is 1 over 1 minus x. It will be nice to write this as just the power form. Easier to find the derivative for the second step. And then f prime is equal to the derivative of this guy. So I use the power rule, negative 1 minus x raised to power negative 2. And where is this negative 1 from? It's from the derivative of the inner function 1 minus x. So minus sign will be gone, and we are left with 1 minus x raised to power negative 2. And then f double prime, you just find the derivative one more time from the f prime. So you get the 2 times 1 minus x to the negative third. Well, the negative sign disappear because one negative sign will come from the derivative of inner function. And you will see the pattern once you find the third derivative. If you find the third derivative, you see that negative 3 times 2 times 1 minus x raised to power negative 4. There's a negative sign coming from the derivative of inner function, so which is 3 times 2 times 1 minus x to the power negative 4. And just this is the same as saying 3 factorial, right? 3 factorial, 1 minus x to the negative 4. This 2 is actually the same as 2 factorial. Now the second column that I have here is to compute my the derivative at a. So in other words, in my formula, I'm computing all these values in my second column. So f of a would be, plug in 3 here, 1 minus 3 raised to power negative 1, negative 1 half. And f prime at 3 is, so plug in 3 in this derivative, and you get negative 2 raised to power negative 2. Similarly, f double prime at 3 is 2 factorial, so plug in 3 in here. So plug in 3 here, so you have 2 factorial, negative 2 raised to power negative 3. Similarly, f triple prime at 3 is 3 factorial, negative 2 times raised to power negative 4. Right, the last column that I'm gonna do is to find those CIs. If you can record all those CIs are the coefficients. That's what we are trying to find. Okay. So C0 is f of a, which is negative 1/2. C1 is negative, which is f prime of 3, which is this guy. Starting from C2, you have to divide the corresponding factorial. So f double prime at 3 divided by 2 factorial. And what is f double prime at 3? It's coming from the left column here, the middle column here. So which is 2 factorial negative 2 raised to the power negative 3 divided by 2 factorial, and 2 factorial cancel. And therefore you have negative 2 raised to the power negative 3. And to find C3, which is right here now, so you use f third triple prime at 3 divided by 3 factorial. And f triple prime at 3, which is this guy, there's a 3 factorial here, so the 3 factorial will be cancelled. We're left with negative 2 raised to the power negative 4. You can see a nice pattern now, right? You can see a nice pattern. Therefore, I do expect you to see this pattern so that you can just quickly write C4 is going to be negative 2 raised to the power negative 5. And you can see that C5 is negative 2 raised to the power negative 6. So that's the C's, or the CI's. So after that, you can now write the Taylor polynomial of 1 over 1 minus x into this power series. So negative 1/2 plus 1 over negative 2 square x minus 3 plus my next coefficient is coming from here. That's my next coefficient C2, okay, which is C2 times x minus 3 raised to the power 2. And the next coefficient is coming from here. Okay, so this is my next coefficient times x minus 3 raised to the power 3. And you quickly can observe that that the power, the relationship of this power, if you look at this pattern, like the power for negative 2 is always 1 more than the power for x minus 3. So therefore, if I call the power for x minus 3 as k, like here, then this would be k plus 1. I start k with 0. So this is what I have. Okay. Now, you see this is k and this is k plus 1. So it's nice to isolate the power 1 and bring it out of the summation notation so that they are both power k right here, right? Both power k. That's the reason I move out the isolates this one. Now it's here. And then after I move that out, both are power k, I can actually group them together. So that's the power series for 1 over 1 minus x. Okay, so that's pretty much it. And speaking of the interval of convergence, and you can certainly use ratio test. But here I choose the roots test because I see the power k. So I apply the roots test here. And now one thing that I on purpose did not write on my original writing here is I want to emphasize it now with you. So what's missing here is the absolute value symbol. You have to consider the absolute value symbol because x can be some number, any number. We want to figure out the number so that it converges. So this result can be negative. That's why we want to have the absolute value sign here. So after the kth roots, this is what we have. And then we get to this inequality. And at the end, we solve for the inequality. We get this interval. Actually, the minus 3 should be gone there now. Okay. And then I check the endpoints. Both endpoints. Where do you plug in? You should plug it in into, so plug this x to the x equals 5 into this power series, and it turns out to be negative 1 raised to power k and summation, which will diverge. Similarly, if you check the other endpoint, it will also diverge. So the interval of convergence is actually this guy from 1 to 5, excluding the endpoint. So this concludes this example.